Okay, good. So we did the integral over x. Now let's do the integral over d4y. So integral over d4y. So what do we have? We've got an integral. Now, where's the y's? There's the d4y. So we'll go d4y. We'll have an e to the I, y dot. And now let's see what terms we have. Well, there's a y sitting there. There is a y sitting there. There is a y sitting there. And there is a y sitting there. So what will we have? We'll have, from the first one, it'll be P2 plus, from the second exponential, P3, from the next exponential plus P4, and from this last exponential, notice that this is an e to the minus I P5 dot y. So we'll have minus P5, okay? And then you use the same identity to get 2 pi to the power of 4 delta to the 4 of P2 plus P3 plus P4 minus P5. Good. Okay, let's interpret these delta functions. Actually, let me draw this Feynman diagram a little larger at the bottom here. That'll help us to interpret it. So here we are, and there we are. Good. So there's our Feynman diagram. We said here we had P1 flowing. Here we had P2 flowing. Here we had P3 flowing. Here there was P4 flowing. And out here we had P5 flowing. Now, at this vertex over here, the one that I've colored in red, if we want the conservation of energy momentum, so the conservation of, I'll write energy momentum as P mu, that tells us the momentum flowing into the vertex, which is P1, must be equal to the momentum flowing out of the vertex, which is P2 plus P3 plus P4. And this must be the case for every component of the 4 momentum. So what we can see is, we integrated d4x, which is the vertex that we're looking at, and that integral over x enforced the conservation of momentum at that vertex. And in a similar way, if we want the conservation of momentum at the second vertex, which was labeled y, then the conservation of momentum here says the momentum flowing into the vertex, which is P2 mu plus P3 mu plus P4 mu, well, that has to be equal to P5 mu. So by integrating over the position of that vertex, by integrating over y, we have enforced energy momentum conservation at that vertex. In every Feynman diagram, you integrate over every vertex, so you always enforce the conservation of energy and momentum at the vertex. Good. Okay, so now let's write down what we've got for our Feynman diagram so far. Okay, so this is equal to, so we've got the minus 4 factorial IG z squared for each vertex. By the way, I could simplify these factors if I wanted to, but I don't want to, because my goal is I want to read off Feynman rules from this expression at the end. So I want to keep everything separate so that all of the factors have a nice interpretation. Okay, so there's the vertex factor and the factor for equivalent lines. Then I have the integral over all of the momenta. So there's a d4p1, there's a d4p2, there is a d4p3, there is a d4p4 over 2 pi to the 4, and finally a d4p5 over 2 pi to the 4. Then we've got our 2 delta functions that we've just obtained from integrating. So we'll have a 2 pi to the 4 we will have a delta to the 4 of P1 minus P2 minus P3 minus P4. That's the red delta. And then we've got the blue delta, which is 2 pi to the 4 delta of P2 plus P3 plus P4 minus P5. Good, that's the second delta. Then we've got all of the propagator factors, one for each line. So each one is an IZ inverse, P1 squared minus M squared plus I epsilon. Then we've got an IZ inverse, P2 squared minus M squared plus I epsilon. Then we've got an IZ inverse, P3 squared minus M squared plus I epsilon. Then we've got the fourth propagator, IZ inverse, P4 squared minus M squared plus I epsilon. And then we've got the last propagator, IZ inverse, P5 squared minus M squared plus I epsilon. And then all that we've got left are two x dependencies. So we've got e to the minus I P1 dot x1 from the very first exponential. So e to the minus I P1 dot x1. And then from the very last exponential, we've got an e to the I P5 dot x2. So we'll have plus I P5 dot x2. Now, it is trivial to do two of the momentum integrations using the delta functions, okay? So let's use the first delta, and we'll use this to do the integral over P4. So the first delta sets P4 to be equal to, so what will it be? So P4 has to be equal to P1 minus P2 minus P3. So I got that just by reading off where is the argument of this first delta function, which I'm just underlining in red. Where is that equal to 0? Okay, so this is what the first delta function sets. When I do this integral, by the way, the 2 pi to the 4 that's nicely multiplied my delta to the 4 will cancel with the 1 over 2 pi to the 4 inside the D4P4. So that's nice. You again see that our conventions with the 2 pi's are very helpful. Then what we're going to do, we're going to use the second delta. And what does it become? The second delta becomes delta 4. It'll be P2 plus P3, then plus P4, but we know what P4 is. So it'll be plus P1 minus P2 minus P3, and then it will be minus P5. Now, just take a look at this. We've got P2 and minus P2, so those cancel. We've got P3 and minus P3, so those cancel. So after we simplify this, we simply get delta to the 4 of P1 minus P5. And that tells us that the momentum flowing into the whole diagram is equal to the momentum flowing out of the whole diagram. So this is sort of overall conservation of energy and momentum. And we will use this to do the integral over P5. So this will set P5 mu simply equal to P1 mu, okay? So those are the two things we need to do. Everywhere we see a P4, we're going to replace it by P1 minus P2 minus P3. And anywhere where we see a P5, we're going to set that equal to P1. And once again, the 2 pi to the 4 in front of the delta function will cancel with the 1 over 2 pi to the 4 from the integral d5P1. Great. Okay. Try to write down the answer. Once you've written it down, start watching the next recording.